So I think we can start. We're ready. Thank you again, everybody, for joining us today. Welcome to this month's ISFE webinar entitled Superheated Steam Drying of Foods, Some Recent Advances, by Dr. Sakamon Devahastin, whom is currently a professor in the Department of Food Engineering at King Mongkut University of Technology, Thonburi in Bangkok, Thailand. His main research interests are in both thermal and non-thermal processing of foods and biomaterials, in particular, the development of a study of novel drying technologies for heat and oxygen-sensitive materials, and also material properties and structural characterization, as well as computational fluid dynamics and heat mass transfer. He has so far published more than 200 papers in referred international journals and given more than 100 presentations at various international conferences. He is an author and co-author of 17 book chapters, author and editor of 4 books, and co-inventor of 4 patents. He has also served as editor of the journal Drying Technology and been on the editorial boards of various other journals in food and thermal engineering. Among the many awards bestowed upon him, Dr. Devahastin has awarded the Young Technologist Award by the Foundation for the Promotion of Science and Technology under the patronage of HM, the King of Thailand, in 2004. He's also the recipient of the 2012 National Outstanding Researcher Award from the National Research Council of Thailand, the 2014 Award of Excellence in Drying from the French Drying Association for Industry and Agriculture, the 2018 Ajinomoto Award for Outstanding Food Science and Technology Researcher from the Ajinomoto Foundation and the Food Science and Technology Association of Thailand. Dr. Devahastin is the recipient also of the 26th Thailand Torrey Science and Technology Award, which was given by the Thailand Torrey Science Foundation in 2019. He has been elected Associate Fellow of the Academy of Science of the Royal Society of Thailand since 2016. He has also received his PhD in Chemical Engineering from McGill University in Canada in 2001. Before we start, please remember to mute your microphone during the presentation. If you have any questions through it, you can write them on the chat so that you do not forget them. And at the end, you can ask them directly to our speaker, but I can also read them aloud for you. And well, thank you and welcome. Again, thanks for your time, Professor Sakamon, and now it's your audience. Thank you all for being here. I think you're muted. Perfect.
Thanks a lot for your kind introduction, and good morning, good afternoon, and good evening, everyone. I don't know you are around the world, so I just say good morning and good afternoon, good evening. It's my pleasure to be able to talk to you today about superheated steam drying, which is something that I have been working on for the past 20 years or so. So I hope that I can give you some idea about this interesting technology and some advances that the people around the world, and in particular our lab, has been making. So I think I can share the screen. All right. Is it all right? Is it okay?
Is it okay? Yeah, it's okay.
Yeah. Okay. So as I mentioned, the title of the talk today is on superheated steam drying of foods. And I said some recent advances because I want to emphasize on something that we have been doing during the past few years, including the scaling up of the so-called low pressure superheated steam drying from lab scale equipment to an industrial scale dryer. So first of all, I'll give you some introduction about superheated steam drying. Someone may have not heard of that or may not be so familiar with that. So I'll just give you a very quick overview of the technology. And then I will talk about superheated steam drying of foods and biomaterials in general. And then I will focus more on low pressure superheated steam drying or LPSSD. And then I'll show you some example of what we have done. As a technology itself, superheated steam drying is not a new technology at all. It was proposed more than 100 years ago. And actually, if you check up the literature, you will see that there was a book published in Germany in 18 something. And the title of that book was Drying Using Hot Air and Superheated Steam. So the technology itself is not new at all. However, the technology received attention only during the past, I would say 30 or 40 years, starting probably at McGill University when people use superheated steam drying to dry a paper, pulp and paper. And then people in Europe, of course, they use superheated steam drying to dry coal, to dry peat, and some biomass. The concept of the technology is, I mean, the concept is very simple. Instead of using hot air as a drying medium, you just use superheated steam. And what is superheated steam, by the way? Superheated steam is just steam that has a temperature higher than the saturation temperature of water at a particular pressure. So for example, at 1 atmospheric pressure, at 1 bar pressure, I'm sorry, saturation temperature is 100 degrees Celsius. So if you have steam with the temperature higher than 100 degrees Celsius, then you have superheated steam. The concept is easy like that. And please note that the steam that you see coming out of your kettle at home, that is not steam, that's water droplet. Okay, you see the steam and water droplet mixing together. However, if you heat up that steam, which is called saturated steam, by the way, you heat it up and then you evaporate water droplet, you see nothing, okay? Because steam itself is transparent. It's very clear, it's clear, transparent, so you don't see it. But that superheated steam is not stable from thermodynamic point of view. It's not stable. It always want to go back to saturation temperature. And what is the easiest way for the steam at higher temperature to go back to saturation temperature? The easiest way is to picking up water, cool itself down, and then become saturated steam again. And so that is why we can use steam, which is water, to remove water from food material, okay? Because when you introduce superheated steam into the drying chamber and superheated steam is in contact with your drying product, superheated steam will transfer heat to your drying product, and the water in the drying product will just evaporate out, and that superheated steam will pick up water, cool itself down, and then become saturated steam and leave the dryer. And that's the concept. So it's very simple. In theoretically, it's very simple. However, in practice, the system is more complicated than the hot air drying system, because, for example, you cannot allow leak here and there, like in the case of, hot air dryer, especially at a large scale dryer. You cannot have air entering the system. Like in the case of continuous dryer, you have like a conveyor dryer, for example, and then you bring in the drying product. You can, of course, you can entrain some air into the dryer, not a big problem. But in the case of superheated steam drying, if you somehow suck the air into the drying chamber, the efficiency of the drying process will drop significantly, and that is a problem. So in practice, superheated steam drying system is a little bit more complicated than hot air drying system. However, this drying system offers some advantages which are of interest. First of all, in terms of energy consumption, if okay, it's a big if exhaust steam can be used elsewhere in the process, the system will have lower net energy consumption compared to hot air drying. I'll talk about this a little bit later. Also, another advantage, which is very interesting actually, is that in many cases, product quality, dry product quality is better when you use superheated steam to dry your product when compared with hot air dry product. Here is a very simple schematic diagram of superheated steam drying system. Let's say you start from boiler, okay? A boiler may generate a saturated steam at whatever pressure. Let's say 8 bar, and then you can reduce it, of course, to just a little bit above atmospheric pressure. You pass this steam, saturated steam, to a heater here, and then you heat it up to make it become superheated steam. And then you can introduce this superheated steam into the drying chamber, where you have a drying product. As I said, superheated steam will transfer heat to the drying product. Water in the product will evaporate, and then superheated steam will pick up the water, cool itself down, and then leave the drying chamber as saturated steam. And then, of course, you can recycle the steam in a closed loop here, okay? And then you can heat it up again to become superheated steam, and you can use it for drying again. So if you can do that, that means the latent heat of vaporization will not be lost. You can always maintain the latent heat of evaporation. The only additional energy that you have to put is here at the heater, which is sensible heat. So compare with hot air, where you cannot easily or economically recover the latent heat of evaporation. Superheated steam drying system will consume much less energy if you can recycle the steam like that, because steam is still steam. Okay, you generate steam only once, and then you can keep recycle the steam. Or if you do not want to do that, you have some other use of steam. You can purge the steam out, and then you can use it for some other application. In that case, you also should not charge the energy consumption of using steam elsewhere to the drying process. Or if you don't want to use the steam directly, another thing that you can do is you can condense it in a condenser. You get the condensate, and you can use condensate for some other application. You can use it for cleaning, or you can use it for blanching or whatever. Again, if you do that, you shouldn't charge the energy consumption to the drying process. And this is the reason why superheated steam, when compared with hot air drying, will have lower net energy consumption. I say net energy consumption, okay? You can even take a look at this diagram. So for example, if you start with saturated steam feed, let's assume that the temperature is 100 degrees Celsius at 1 bar pressure. The enthalpy here is about 2690 kilojoule per kilogram. And you can pass this steam to a heater. Okay, you can use gas heater, you can use electric heater, whatever. And then you heat it up, let's say only 210 degrees Celsius at the same pressure. Enthalpy increases to 2720 kilojoule per kilogram. And then you can use this you can use this superheated steam to dry your product, which is in the drying chamber here. And then at the outlet of the dryer, you get saturated steam again, okay, back to 100 degrees Celsius, and the enthalpy is back to 2690. So if you want to heat it up again, you only need to add only 30 kilojoule per kilogram of steam. So you can see that you can save a lot of energy. So this is one benefit of using superheated steam drying. Actually, during superheated steam drying, there are two important phenomena that take place. The first one is that you will have initial steam condensation. And why is that? Well, because let's just imagine if you have drying product sitting in the dryer at room temperature, or a little bit higher than room temperature, let's say 30-35 degrees Celsius. And then you introduce superheated steam at 100 something degrees Celsius into the drying chamber. Of course, you have condensation of steam on the surface of the cooler drying product. Okay, and that steam condensation will lead to some increase in the moisture content. Well, you will say that, okay, I'm doing drying here. Why should some increase in moisture content is a good thing. Well, in some cases, it's a good thing. I will talk about it a little bit later. And along with the slight increase in the moisture content, you will also have a very rapid increase in the surface temperature of the drying product, because the steam upon condensation, it releases the latent heat to the drying product. So the temperature of the drying product goes up very quickly. Again, there's some benefit of having that rapid temperature increase. The second phenomenon is that you will have negligible amount of oxygen in the drying chamber, because when you blow the superheated steam into the drying chamber, superheated steam will just purge out all the air and then fill out the chamber. And so you will have more or less no remaining free oxygen in the drying chamber. You may have some 2-3%, but quite low anyway, compared to 21% as in the case of hot air drying. And when you have no oxygen, it means that you will have negligible amount of oxidation reaction, like enzymatic browning, lipid oxidation, or some vitamin degradation. So product quality in many cases is better than hot air dry product. If you take a look here, for example, we have a drying curve, green line here, and the temperature evolution curve, the blue line here. And you see that at the beginning, you have some jump in the moisture content here, the area that I put a circle here. And this initial condensation, as I said, comes with the rapid temperature rise due to condensation. Just imagine what would happen here. If you have a starch product, okay, if you have a starch-based product, the starch normally we gelatinize at a temperature of, I don't know, 60-70 degrees Celsius. And in the case of hot air drying, even you use very high drying air temperature, the temperature will go up not as quickly as this one. We just go up slowly. Okay, so when you still have water for the gelatinization to take place, you don't have enough temperature. So the temperature is not high enough for the gelatinization to take place. But once you have reached the temperature where gelatinization can take place, you don't have enough water for the gelatinization to fully take place anymore. So gelatinization in the case of hot air drying will not be as complete as in the case of superheated steam drying, where you have a very quick increase in the temperature. So the temperature reached here, for example, saturation temperature at 1 bar, which is 100 degrees Celsius. So temperature is more than enough for gelatinization. And at the same time, you have water, okay? Because temperature goes up very quickly here, and you still have a lot of water, both from condensation and from the fact that the drying process just started not long ago. So you have much better gelatinization, okay? And this is very, very beneficial when you dry many types of starch-based product. Another thing is that you have a lot of water inside your matrix, and that water will boil within the material, because the temperature, as I said, goes up very quickly and reach the saturation temperature, which is 100 degrees Celsius when you operate the dryer at 1 bar pressure. When the water evaporate or vaporize, its volume will increase like 1,000 times. And what happened was that the matrix or your structure will be pushed and then expanded quite a lot. So at the end, you have a lot of pore or empty spaces inside your product, and this pore empty space will cause the porosity to increase and affect the texture in a desirable fashion. Your product will become more crunchy, and if you try to rehydrate that product, rehydration will be much better than hot air dry product, because you have a lot of pore and you have a lot of empty spaces. And that is because of the rapid temperature increase along with the availability of water during the initial period of drying, which is not possible in the case of hot air drying, because in the case of hot air drying, again, in the beginning you have a lot of water, but temperature is still low. Water would not vaporize. But at the time when the temperature of the product is high enough for water to vaporize, you don't have water left to vaporize anyway. So that's a problem, or I wouldn't say problem, but limitation of hot air drying. And the temperature will remain here, okay, at the saturation temperature until you have reached the critical moisture content and you start to enter the so-called falling rate period. Okay, temperature will stay at saturation temperature of steam during the whole constant drying rate period. In the case of hot air drying, this temperature is the wet bulb temperature. But in the case of superheated steam drying, it will be saturation temperature of steam. And once you start to be in the falling rate period, the temperature will start to rise and then eventually approach the superheated steam drying temperature. So that is what happened during the superheated steam drying process. Here, I mentioned this already. So as I said, normally, okay, superheated steam drying would yield higher product porosity due to the evolution of steam within the product, and that result in turn in lower bow density, which aid rehydration, make rehydration behavior more superior. And we found that in many cases, case hardened skin that is likely to form during hot air drying is less. In the case of superheated steam drying, probably because steam try to move from inside to outside and leave the structure more porous, leave the skin more porous. And because of the lack of oxygen, no oxidative reaction is possible. So color and many types of nutrients are better preserved. And if you remove toxic or organic liquids instead of water, those toxic or organic liquids can be more easily recovered because they are a non-polar compound, and skin is and steam is polar compound. So you just need a simple decanter to separate the organic liquid from the condensate. Another interesting thing is that you can perform other heat treatments like blanching or boiling or cooking or even sterilization, even deodorization and microbial inactivation simultaneously with drying, because you are doing drying at a relatively higher temperature. You can do parboiling of rice at the same time as drying, for example. And in our lab, actually, we proved that we could prepare parboiled rice in a matter of minutes when compared with the traditional process, which require like hours to prepare parboiled rice. In terms of energy, as I mentioned, if we can recycle the exhaust steam or we can use it elsewhere in the plant, the latent heat should not be charged or should not be counted as the energy consumption of the drying process. And that would lead to the net energy consumption of superheated steam drying of only 1,500 kilojoule per kilogram of water removed, which is, I don't know, 3-4 times lower than in the case of hot air drying. Don't forget that hot air drying is not 2,500 kilojoule per kilogram. Okay, that's latent heat of vaporization of water, but in the real drying process, the energy consumption is more than that. So reduced net energy consumption is one clear advantage of superheated steam drying. And actually, this is the data numbers from a company in Canada. And you can see that in the case of conventional hot air drying process, you require much more thermal energy than in the case of superheated steam. Of course, you may require a little bit more electricity in the case of superheated steam, because you may need a larger blower, for example, for superheated steam drying. But in terms of thermal energy and in terms of overall energy requirement, the energy requirement for the superheated steam is much lower. Well, every process has pros and cons. And what about the disadvantages of superheated steam drying process? As I said, the system is more complicated than hot air drying system. Another important disadvantage of this drying technology is that products that may melt or undergo glass transition or be damaged in any way at saturation temperature of steam cannot be dry using superheated steam dryer, typical superheated steam dryer. We have solution for this. I will mention that toward the end of the presentation today. But if you stick to conventional or atmospheric pressure superheated steam drying process, this is the limitation. Another important limitation is that limited knowledge and experience on superheated steam drying are available, because the technology, although it was proposed a long time ago, not many people have adopted it, especially at industrial scale. So there's some limitation, but this is getting better because more and more people are working in this area right now. There are companies that provide superheated steam dryer right now, both in Asia and in Europe. And we hope the situation will become much better in the near future. And in principle, you can apply or you can transform any convective dryer into superheated steam dryer. So any dryer that you introduce hot air directly into the drying chamber, and that hot air is in direct contact with the drying materials, is called convective dryer. You can convert it into superheated steam, at least in principle. So you may see fluidized bed superheated steam dryer in Europe. There's some of them. You see a rotary superheated steam dryer in Australia, in New Zealand. You may see some of them. You may see flash dryer or pneumatic dryer operated using superheated steam dryer, superheated steam as a drying medium. Conveyor dryer. This is available commercially from a company in Japan, for example. And even superheated steam spray dryer, which is something that many people are working right now. And there's a group in New Zealand, there's a group in Germany, there's a group in Japan, and our group are working on superheated steam spray drying at the moment. So possibilities are there. Now, in terms of food products, superheated steam has been applied to food product only about 20 years ago. And the reason is that superheated steam drying of food give us several advantages. For example, there's lack of oxidative reaction. So you have ability to maintain color, nutrients, and you get product of higher porosity, as I mentioned. You also have ability to inactivate microorganisms in a much more effective way, effective fashion than using hot air drying. And you can conduct many heat treatments at the same time as drying. You can do boiling, or parboiling, or blanching at the same time as drying. So instead of having 2 units in parallel, for example, I'm sorry, in series, for example, you can combine blanching unit and drying unit into only 1 unit if you use superheated steam as a drying medium. I'll just give you an example. This is result quite old, actually almost 20 years ago, but it still gives some good idea about what superheated steam drying can do. Here, a group of people in Japan, they dry potato slices in the dryer here, and here they have a very nice setup where you can operate superheated steam drying and hot air drying in the same setup, so they can compare the 2 drying processes in the same setup. It's a fair comparison, actually. And you can see the drying curve here. In the case of hot air drying, the drying curve is just starting here and then go down. It's a nice exponential curve as we are familiar with. But in the case of superheated steam, you have some increase in the moisture content at the beginning here, as I mentioned, and then the curve just go down as usual. But what is more interesting is that the microstructure of superheated steam dry and hot air dry product are quite different. Let's say at 170 degrees Celsius here and 170 degrees Celsius here. Okay, same temperature. In the case of superheated steam, you don't see any starch granule anymore. But in the case of hot air drying, you still see a lot of starch granules. And this is because, as I mentioned, if you use superheated steam, you have initial condensation, you have a lot of water, and the temperature is there. So you can have a much more complete gelatinization of starch, as opposed to the case of hot air drying. You cannot have a complete gelatinization of starch, so you still see a lot of starch granule. And in terms of porosity, if you look at the right picture here, superheated steam, in the case of superheated steam drying, you see a lot of pore. Okay, you see a lot of opening. In the case of hot air, you see a thick crust here. It's a very thick crust here. So just imagine if you have to bite through this potato slice, hot air potato slice, it will be very hard. It will be quite hard to bite through. Or if you want to rehydrate this for some reason, the water cannot go into the pore easily. So the rehydration behavior or capability of this hot air dry potato slice would be much more inferior than the superheated steam dry potato slice. And this is the advantage of superheated steam drying. And you can apply this to all kinds of snacks, actually. Fruit snacks doesn't have to be only starch-based product, but can be many types of fruits. And actually, people try so many things. People try using superheated steam to dry potato chips, tortilla chips. But the problem, one big problem is that there's no oil on the surface, so it's quite difficult to apply other ingredients like salt or some seasoning. So some company they have to spray some oil on the surface of the steam dry potato chips. So at the end they feel that it's not worthwhile. So they go back to frying because they have to put the additional oil on anyway. So although the texture of potato is good, it's very similar to fried potato, but you cannot apply seasoning or salt or whatever, and people won't like it, unfortunately. In our lab, we try superheated steam drying with shrimp. Like in the case of shrimp, it's very interesting because if you want to produce dry shrimp, normally you have to boil shrimp in salt solution first, and then you dry it. But if you use superheated steam drying, you can just dip or soak shrimp in salt solution, and then you can put in the dryer directly, and you get dry shrimp in one step. In people in Canada, they dry Asian noodle, they dry soybean, they dry spent grain from brewery using superheated steam. In Thailand, also in another lab in the same university as mine, they use superheated steam to dry paddy. They use superheated steam to prepare parboiled rice. There's some work that use superheated steam to dry cocoa. I'm sorry for the wrong spelling here. They use superheated steam to dry coffee, to dry cocoa. And in our lab, we try superheated steam to dry vegetables and fruits and herbs, but we found some problem here because fruits and vegetables, and especially spices and herbs, are normally damaged at saturation temperature of steam at atmospheric pressure. So we cannot use conventional atmospheric pressure superheated steam to dry this product. So need exists actually for a low pressure system for heat sensitive product. So we did that. Actually, we combine, because we want superheated steam. Okay, we want all the advantages of superheated steam, like no oxygen, ability to produce high porosity product, the lack of oxygen. We want it, but we do not want superheated steam at higher temperature. So we go back to the definition of superheated steam. What is the definition of superheated steam? Is steam at a temperature higher than saturation temperature. But it doesn't say anywhere that saturation temperature has to be 100 degrees Celsius. If we reduce pressure, it's some simple physics. If you reduce pressure, water boil at lower temperature, that means saturation temperature is lower. Then we get the saturated steam and superheated steam, of course, at lower temperature. So we use this idea to come up with the so-called low pressure superheated steam drying, or LPSSD, which is a very simple combination of vacuum drying and superheated steam drying. So we operate the dryer at reduced pressure. We get saturated steam at lower temperature, and we can use the system for all kinds of heat sensitive products like herbs, spices, fruits, vegetables, and other biomaterials like biopolymers, chitosan, gelatin, something like that. Our lab started working on LPSSD about 20 years ago, and we test this drying system with all kinds of products. And we're quite happy with that. And some of the product are of higher quality than even a freeze-dried product. But the problem is we have a very small setup in our lab. This is the schematic diagram of the LPSSD setup. So we have a boiler here, and then we introduce saturated steam at a lower pressure, let's say 1 bar or 1.5 bar, into the drying chamber. And this drying chamber is actually attached to the vacuum pump here. So this chamber is evacuated actually. So once we introduce the superheated steam, we introduce the saturated steam into the evacuated chamber, the steam will automatically become superheated steam because of the lower pressure. So for example, if we maintain the pressure inside this chamber at 10 kilopascal, saturation temperature should be only about 40 something degrees Celsius, 45 degrees Celsius. So steam entering the chamber at 100 degrees Celsius will for sure become superheated steam by itself. And this is the photograph of the drying system that we have in our lab at the university. And this dryer can dry probably 1 banana at a time. Okay, maybe 5-10 pieces. And of course, no company can afford to dry 5-10 pieces of banana or fruit at one time. So we have to scale this up. And here before I go to scale up, I just want to show you the picture. Here we compare hot air drying and low pressure superheated steam drying, and we use banana as the test material. And you can see that here we didn't treat banana in any way. Okay, we didn't blanch it. We didn't put any chemical like citric acid or sodium metabisulfide or any chemical to treat banana. We just slice the banana and put the slices in the dryer directly. And you can see that in the case of superheated steam drying, the banana has a very nice color. Okay, and this is because of the lack of oxygen in the low pressure superheated steam drying system. So you have no enzymatic browning. And if you can pick up the banana from the screen here, your computer screen here, and then you try to bite it, you will feel that this low pressure superheated steam dry banana is very crispy, almost the same as fried banana, but no oil. Okay, so this is a healthy fruit snack. But if you try hot air dry product, it's very hard, and the color is not nice at all. So company was interested in the technology, but they want something bigger than what we have in the lab. And actually, the company called Natural Producers is a small company in Thailand. It's a brand new company, just started about 3-4 years ago. They expressed their interest in commercializing LPSSD for the production of dry fruits and vegetables. So they want us to help with the design, with the fabrication of the dryer, and with the testing of the dryer. It was a very challenging work actually, because no field experience on this technology was available. We never try to scale the dryer up to a very big industrial scale dryer. We used to work only with small dryer that can put on a desk, for example. So very challenging, and we spent 3 years to come up with something like this. This is an industrial scale dryer. The diameter here is about 2 meters. The length is about 3 meters. And you can see that there are a lot of accessory here, which I don't have time to explain. But if you open the door, this is something that you will see. We can put the cart here, and the cart will carry a lot of trays where you put the dry material on, and you have a steam spray tube here. You spray saturated steam into the drying chamber, and in order to maintain the steam temperature at whatever value that we want, we have a steam heating coil. Okay, in our lab at school, we use electric coil, but at industrial scale, we use steam at a higher pressure running inside the coil to maintain the temperature of the steam. And then, of course, we attach or we connect this drying chamber to a vacuum pump. Here we try banana, and this is the product that we have. Look quite nice and very crispy. And on the right hand side here is what you call, I mean, at least people in the UK call plum mango. It's not mango, but it's not plum and it's not mango. It's called plum mango. It's very tasty, tropical fruit. It's available in Thailand only for a few months, so we had to dry it only like the month of March and April, and we could get a very nice product using this dryer. We also try many different other products like apple, like banana here. This is pumpkin. This is pineapple. This one is ginger. This one is galango. Galango is in close family to ginger. This is lemongrass. Is popularly used in many Thai cuisine. And you can see the color is very nice. It's very similar to the fresh product actually. We could even dry coconut. This is sliced coconut, and we dry it. Actually, we don't have to dry it to brown like this. Okay, if we dry it only to the moisture content where we can have a safe storage moisture content, browning will not be there. But then the customer said that they don't like dry coconut without browning, so we have to deliberately extend the drying time to make the product brown like this. But actually we didn't have to if we don't want to. This is durian, durian chips, very crispy and smell almost like fresh durian. And here on the right hand side is 3 kinds of vegetables. This is pandan leaf. The middle one is pandan leaf. The far right here is lime leaf, and the lower end here is basil leaf, dry basil leaf, and it can rehydrate very quickly. And actually, when you do some cooking, normally if you have dry basil leaf, you have to rehydrate it in water first, and then you use it in curry or in stir fry dish. But for our product, you just throw in the dry leaf into the pan, and then you can continue cooking right away, because it will just absorb the sauce or gravy and then rehydrate by itself. We could also produce all kinds of color powder. Here we use different types of fruits and vegetables, like pumpkin, like carrot, like purple cabbage or beetroot, to prepare powder. So we dry the starting material first, and then we grind it into powder. And here, take a look at the green powder, for example. We use green powder to prepare cookie dough, and then we bake cookie, and then you can see that the green color is still there, it's not fading away. And actually the color stability is even better than that of a synthetic color gel. If you use green color gel, you put in the dough, and after you bake it into cookie, the green color will fade away quite a lot, actually. Some people may ask, what about microbial inactivation up on low pressure superheated steam drying? Well, we test the capability of 3 drying processes to inactivate microorganisms. Here, we inoculate Salmonella on the surface of cabbage. And picture A here is the fresh sample. We inoculate Salmonella here. And then up on hot air drying, figure B here, you can see that you still have some intact cell. Okay, some cell may look damaged, but you still see some intact cell. If we use vacuum drying, some cell were damaged. Okay, and if we use superheated steam, cell damage is was 100%, and the time that required for more or less complete microbial inactivation was much shorter than in the case of hot air drying. Okay, all these 3 drying processes were conducted at the same 60 degrees Celsius. So temperature were the same, and drying time in the case of superheated steam drying was much shorter than in the case of hot air drying. So microbial inactivation is also very effective. Again, because during the initial period of drying, you have high water activity and you have high temperature. So microbial inactivation is very effective. So I guess in the end, I will not say much. I'll just say that there is still much room to play with this technology. We have been using this technology to produce fruit snacks, plant-based meat ingredients, food powder. There are, of course, many other things that I couldn't think of yet, but you may be able to come up with some new idea of your own. So you're welcome. And it would be nice of you if you can come up with some good idea, and then you share your idea with me, either through submission of manuscript to Drying Technology. And we look forward to reading your work on that. Thank you.
Thank you so much, Dr. Devahastin, for sharing your knowledge with us. So let's start the question and answer session of the webinar. Remember to turn on your microphone to ask a question directly. And I already have some for you in the chat. So anyone that would like to ask directly. Okay, so let's start with the ones in the chat. This one is from Dr. Mahendran, and he says, what is the percentage of brokens when SSD used for parboiling of rice? Normally, it is 5% in the case of steam parboiling. So since SSD parboils at short time, will it increase the broken percentage?
Not really, because we found that when we have starch gelatinization, you know,